In this lesson, we begin to examine our first bona fide organic reaction, namely the nucleophilic substitution reaction. So the following reaction is known to take place. If you take ethyl bromide and react it with sodium methoxide, you will get ethyl methyl ether plus sodium bromide. Okay? This can be thought of as a double displacement reaction of sorts, putting it into the context in which you start to learn reactions in general chemistry. A double displacement reaction is a reaction of the form AB plus CD gives AD plus CB. And in this case, A is the ethyl fragment, C2H5, B is Br, C is Na, and D is OCH3. So we end up with C2H5A, OCH3D, and NaCBrB. From the perspective of the organic fragment, a substitution is taking place. You are removing Br from the organic molecule, from the ethyl group, and you are sticking OCH3 into its place. So eliminating the Na, which is a spectator ion, this is an example of a very general class of reactions. Organic chemists refer to the kinds of molecules such as alkyl halides that undergo these reactions using the shorthand Rx, where X is called the leaving group because it is that which leaves when the substitution happens, and Rx reacts with Y, where Y is called a nucleophile, also known as a Lewis base. And the products, of course, are Y. Y is part of the organic fragment, and X minus. So when we start thinking about a chemical reaction, we're going to need to answer some important questions. We already answered the question of what happens. We will now turn our attention to why it happens, and then turn our attention to the much more complex question of how it happens. So this reaction is a spontaneous reaction. If you mix these two chemicals together, you will get reaction happening. So in order for any spontaneous reaction to take place, the products must be more stable, meaning lower in energy, than the reactants. So this is one way to think about this is through the acid-base concepts that we've been developing through some of the previous lessons. No, this is not an acid-base reaction. However, if we look at what the product is versus, or at least what one of the products is, versus what the starting material is, we are starting with OCH3 minus and ending with Br minus. And Br minus is a much weaker base. Br minus is the conjugate base of HBr, which has a pKa of -9, whereas OCH3 minus is the conjugate base of CH3OH, which has a pKa of 16. The fact that we are generating a much weaker base in the course of this reaction serves as the driving force for this reaction. Okay, so now, what is the mechanism of this reaction, or how does the reaction take place? Well, to start with, looking at one of the products, the fact that Br minus is a product of this reaction, we know that the carbon-bromine bond must cleave heterolytically with both electrons going on to the bromine. Similarly, we can also come to the conclusion that both of the electrons in the new carbon-oxygen bond must come from the oxygen. Why? Oxygen starts out in OCH3 minus with 3 lone pairs and a negative charge, and in the ether product, it ends up neutral with 2 lone pairs. Secondly, carbon is capable of accepting 2 electrons, so those 2 electrons can come to the oxygen because carbon is giving 2 electrons to the bromine during the heterolytic bond cleavage. Next question we want to consider then is, what is the order of events? We know that the bromine has to leave. We know that the OCH3 has to come in, but how does it happen? Well, there are three possibilities. The first possibility is that the leaving group leaves, and then the nucleophile attacks. So that's going to look something like this. So step one, if we cleave the carbon-bromine bond heterolytically, putting the electrons onto the bromine, what will be left on the carbon will be a positive charge, and we will get a carbocation. Then in step two, there will be a Lewis acid-base reaction between the carbocation and the nucleophile to give the product. Okay? This mechanism looks reasonable. You have seen both of these steps, the heterolytic cleavage, the carbocation, and the Lewis acid-base reaction in previous lessons. Okay, possibility two would be the nucleophile attacks first, and then the leaving group leaves. Okay, so step one of this reaction would have the nucleophile with its lone pair coming and attacking the carbon and forming an intermediate with, oh no! Stop right there! 5 bonds to carbon. No, 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 not reasonable at all, and we have to put a big red X through this mechanism. Okay, I'm better now. If that's not a reasonable mechanism, what is the third possibility? Well, that would be loss of the leaving group first. Loss of the leaving group and attack of the nucleophile taking place at the same time. So what this looks like, it will start out looking the same as the previous unreasonable course of events, and that the nucleophile does attack the carbon bearing the leaving group, but at the same time the nucleophile is attacking, at the same time we're using one arrow to form a bond between Y and carbon, the leaving group is leaving. So we have to use another arrow from the electrons in the CX bond going onto the X. It all happens at the same time. This also looks reasonable. We don't ever come to an intermediate that has 5 bonds to carbon. Okay, so there are 2 reasonable mechanisms, and it turns out that this substitution reaction, depending on various conditions, can take place by one of these 2 mechanisms. So instead of just calling them possibility 1 and possibility 3, that's only something that makes sense in the context of this lesson. All organic chemists want to be able to talk about these mechanisms in a language that any other organic chemist could understand. So the first mechanism is called the SN1 mechanism, and the third mechanism, the other reasonable possibility, is called the SN2 mechanism. What this stands for, S stands for substitution, N stands for nucleophilic, and 1 stands for unimolecular, whereas 2 stands for bimolecular. So in order to understand a little more what unimolecular and bimolecular mean, we have to cover the concept of kinetics of substitution reactions, because these turn out to be how many expressions you have in the rate law. And that's what we will do in our next lesson.